And phi out over phi in equal hs closed loop is actually omega out to over omega in, because the linear operation of phi out phi is equal to omega. Omega equal d dt phi. Just dividing d dt equal disappear, so omega transfer function equal phi transfer function. So we use this hs, h of s, to represent. We can use this to this omega in, omega out over omega in closed loop, which is kpd kvco, kpd kvco. This is omega low pass filter. Omega 0 is in this book. I remember this is low pass LPF, omega LPF, and I didn't remember. I don't remember, so I derived this. So kpd kvco divided by s1 plus s over omega LPF divided by 1 plus this. So this is s plus s over plus no s1 plus s over omega LPF and s 1 plus s over omega LPF plus kpd kvco. This is cancelled, and so equals omega low pass filter is multiplied to here. So omega low pass filter kpd kvco divided by s squared plus omega low pass filter s plus omega low pass filter kpd kvco. This is second order, and s equals minus zeta plus minus square root 1 zeta square minus 1 omega n all over omega n, and omega n equals square root of omega low pass filter times kpd kvco. This is omega n squared, and this is s squared plus 2 zeta omega n s plus omega n squared, where zeta equals what? 2 zeta omega n equal omega LPF, so zeta equal zeta equals omega, so low LPF divided by 2 zeta or omega n, which is half square root omega low plus filter is cancelled over KPD square root of omega sub LPF divided by KPD times K sub BCO. This is zeta and this is omega n, omega sub n. This is pole where zeta larger than 1, they are real, but zeta less than 1, this is imaginary number, complex conjugate here. And the textbook describes when more precisely when zeta is less than 1 and it can oscillate, having some ringing, but decay in a long time. In a long time, the ringing is stabilized. Step response is written, and we need to know the topology and the transfer function of closed loop of S-plane, and we need Laplace transformation, and we need to know the incidential response of this second order pole and transfer function. And so I'd like to recalculate here, try to remembering the Laplace transformation table and to derive the step response for delta omega in unit step response. Delta omega u of t of this system. Many engineers and students know even if they don't know the name initial response, I think we need to know, we need to remember the response and how to calculate in this case. There are many scenes watching this response. So omega n squared s squared plus 2 zeta omega n s plus omega n squared is hs, and step response omega ut of Laplace transformation equals delta omega over s, and this is omega, and for phi we have phi because d phi dt equals omega, so it can be integrated, and delta phi equal integral of Laplace transformation is 1 over s of fs. D phi dt integral to d phi delta phi, which is this fs divided by s equals omega delta omega over s squared. And this time we need this step. So omega out to omega in is this unit step, delta omega equals this times this is omega out. So s times omega omega n squared divided by s squared plus 2 zeta omega ns plus omega n squared is the transfer function for S plane. So omega out divided by delta omega unit function is the inverse of this S plane representation Laplace transformation pattern, which is given this when zeta less than 1, square root zeta square minus 1 is negative and 1 minus zeta square is positive, and there's I imaginary number and plus minus, and there's also minus xi omega n, this is omega, minus xi omega n plus minus I of I times this is S, 2 of S1 and S sub 1 is substitute for this solution. The denominator's solution is this, and so we write S and S minus S1 equal plus zeta omega n plus I square minus 1 zeta square omega n times S plus xi omega n minus I square root 1 minus zeta square omega n, and this is omega squared, and this is simplified omega n squared divided by S plus omega zeta omega n squared, this squared, minus this squared, and minus I squared equal I squared equals minus 1, so plus this squared. And dividing the factor like this is the same. Xi omega n and this is the same. This is omega prime. Say this is omega prime. Omega prime square the same. S plus zeta omega n squared same. Omega plus omega prime squared the same. And factoring this is cancelling out to omega n squared is how? Zeta with this times this and this times this. S pro this is cancelled out from this and this. Maybe this. This here? Alright. No. S. They need S plus zeta omega n. This times this S squared. This times this zeta omega n squared S. And this times this zeta omega n S. So minus 2 zeta omega n S cancelled out, plus 2 zeta omega n S, and S squared cancelled out from this. And there remains this squared, zeta omega n squared remained. So zeta omega n squared remained, but there's also here this, and this is 1 minus z omega n squared minus zeta square omega n squared, which is cancelled out, and remaining omega n squared. So this is 1. then we know the time representation inverse transfer function or inverse Laplace transfer function, this, which is this is 1. This is minus exponential minus zeta omega n t all over times. This is zeta. This is this, and this square is this square, and this is this. We need this is cosine and this is sine, and sine square root 1 over zeta squared times zeta sine square root 1 minus zeta square omega n t plus all over minus all over parentheses closed, and this is cosine factor equal simply cosine of square root 1 minus zeta square omega n t. Because I said I reminding the Laplace transformation table. So last week I watched them. Sine omega t of Laplace transformation is Laplace transformation of this equals omega over s plus omega square, I square plus omega square, and cosine omega t, Laplace transformation of cosine equals s over s time plus omega squared, and if s is shifted to a real number or imaginary number, s in Laplace transformation, so f of Laplace transformation of s plus a, the inverse transformation is ft. Ft is fs, and fs plus a, capital F plus a, inverse transformation is ft times exponential minus at. And if the unit function is transferred, which is 1 over s, and fs ft df dt transfer function equal f of s capital divided by the times s, and the integral of ft is, which is this, is fs over f s. This is plus f0, and using these three, from this we can inverse transformation of the Laplace inverse transfer function. We can write inverse transfer function of this bottom equation. So omega out over delta omega unit function of t equals 1 minus that. 消しちゃった。Or when cosine theta equals zeta and sine theta equals square root 1 minus zeta squared, and the tangent equals tangent is sin cos cosine sine cosine 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 sine. We can write this using, after that we can write this equation, zeta omega n t times sine square root 1 minus zeta square omega n t plus theta, and theta is this, or sine cosine sine this cosine this sine this sine this sine theta. Okay, divided by this sine this sine, where cosine tangent theta equals square root 1 minus zeta squared divided by zeta. We can write this expression in the textbook. In example, they as if this is much less than 1, and this is up nearly 1, and the asymptote of peak value nearly equals sine going to 1 is maximum of sine function, and this is 1, and approximately which time constant calculating for calculating the time constant, what time does it take to stabilize the frequency difference, settling time, zeta omega n. 1 over zeta omega n is locking time, settling time of this. For roughly calculating, they use this is 1 and this is 1, and the example solution is given like that from this equation. So we need to know the transfer function, Laplace transformation table, and how to calculate the inverse transformation of step response. And this feedback loop representation of type 1 PLL. Type 2 is going like the same way. Type 2 for type 2, the analysis is going like the same way as this type 1. So it's easy, and we need to know how KPD, KVCO affect PLL behavior. Then the actual imagination is much more somehow difficult, and we need to one more thing is more important is VCO. What is VCO, and are there any different topologies for VCO? Maybe you know the source coupled VCO using N channel and P channel CMOS, or like described in Jake Baker's textbook. I remember somehow like this. maybe this is ground, this is totally on, and N channel, and this is N channel input, and this is also N channel input, and this is current source, and this is like this source cross coupled, and this is output is there. Where's the output? Where's the output? Wait, voltage, and are there any capacitor there? Capacitor, switch. This is switch, and this is current source, charge and discharge. There's capacitor C, and this oscillates within VDD minus VTHN and VDD minus 2 VTHN, where VDD minus VTHN, when this is N channel, when this is N channel, this is VDD, this need to VDD, so the most largest voltage VD minus VTH here. This is on, and this is VT need to VTH. The most least voltage output is VD minus 2 VTH. So this is output node. Outer node bar, maybe, and the oscillate. We need some buffer. Use maybe self-biased inverter, differential inverter, self-biased one. On the next stage, getting full range, rail to rail voltage, and inverter also to shape the output and make the generating output. Now this is just voltage controlled oscillator, which is controlled here. This current. This current is controlled V cont voltage. Higher current bias and higher oscillating frequency, lower V control makes lower frequency output. So voltage controlled oscillator. Example. And there's another example, very famous, using Varactor diode. And inductance, I don't know where about this, but this is more easy to calculate and evaluate for less than 100 gigahertz version. For 200 or several hundred megahertz frequency VCO, it can be applied. Maybe utilizing usual CMOS fabrication process. And VCO is more important. VCO, how large bandwidth can it linearly generate, and how fast that can it lock the phase and frequency, and how stable, and how and also how less jitter does it generates. but there's a limitation, physical limitation there, and usually it's important in phase noise, with phase noise of VCO. VCO is the resource, comparable resource of jitter of generated output, clock output. Too much jitter, we couldn't get a correct calculation from the semiconductor made system. So there are more and more topic with this PLL. So just the basics and almost elementary concepts and calculation for concepts. So you need to remember this just for type 1, and there's another type 2 described in this textbook. So I need more time for learning English, how to speak in English, how to think in English. More and more time I need. So mathematics is not so difficult for every university students majoring in electronics or physics. You know, it's not so difficult. But designing this is a more and more difficult. But they have designers have many know-hows to actualize the PLL, many types of PLL. So we need experience and know-how, technique, IP knowledge is for good PLL for actual application. But the basics is this. I forgot another thing, important thing. This is just phase lock, and edge is well aligned, and frequency lock, and we need multiplier. Next, I study with this textbook how multiplier synthesizing the frequency is done. Maybe here this is divider. Divided by M is there, so F in is multiplied M of F out. Because if this is F in, this is divided by M. F out divided by M equal F out. And this is F in. F in and F in. F in and F out over M is equalized, synchronized, and locked. And the output is M times the F in. Because feedback loop, in between the feedback, there's a divider of M. 1 over M times 1 over M. This is 2. This is 4. They're usually using some clock. What kind of clock? And divide by. This is divided by 4. This is divided by 16, half for 1/4, 1 over 8 and 16th. So 16th M equal 16. There's 4 D F in between there. But what kind of clock does this? divide it, they need to divide itself in stable operation. So we need to know how to realize divided by n feedback gain circuit. Maybe m to the m log to m equal to the n, so log base 10 of log base 10 and divided by log of base 10 of 2 equals n. And usual normal logarithm of m divided by logarithm 2 solves series DFF needed, maybe clocked by itself. Or how can we do the divide with fast clock? We don't have clock. Another clock. This is slow. This is fast. So we need this clock. And so fast is very slow, and gradually very fast, multiplied by tens of thousands, tens of hundreds of thousands of frequency. So this divider can function in very fast frequency, and you can understand this this time. But how is we need to know. We need to run next time. I don't know so precisely. But if they also there are divider there, or somewhere there, we can fractional frequency PLL. We can make fractional PLL, but I don't know precisely of this. But usually fractional synthesizer is utilized in many applications, so we need to know this MF out over N PLL also. But the simple basic is using divider, multiplying M times F in PLL. We need faster frequency and devices on a semiconductor, more than crystal oscillator outside of the chip. VCO is inside semiconductor on a chip, controlled by voltage, and making faster, tens of hundreds of thousands of faster frequency on a chip.